Hello, this is Miriam Kassem, and I'll be walking you through our very first lab in Physics 2211, which is about constant velocity. Here we have the index. I'll be introducing the lab, explaining the physics involved, outlining the experiment, sharing my code, making comparisons, and finally, identifying sources of error and discussing multiple what-ifs. The purpose of this lab is to track and analyze the motion and position of a cart traveling at constant velocity with respect to time. Using a software called Tracker, we'll be aiming for accurate results that will match our theoretical model that we made using GlowScript. But firstly, let's introduce the physics principles related to our lab. First off is Newton's first law, which states that an object in motion or at rest will stay in motion or at rest unless acted upon by an external force. Secondly, we have Newton's second law, which is commonly known as F is equal to ma, but here it's been rewritten in terms of V instead of A to match our lab objectives. Lastly, we have the conservation of momentum, which states that the momentum before the collision and after the collision must be equal. Now, let's introduce our experiment. We'll be starting off with the equipment we used. We used a cart, a track, meter rulers, a stopwatch, a video camera, and a balance to measure the mass of the cart. It's also important to note that we used this smooth track to lower the friction. Furthermore, we conducted the experiment indoors to avoid wind. After multiple trials, we successfully recorded the cart moving on the track at constant velocity. Initially, we gave the cart a light push to get it moving. This is where the principle of conservation of momentum is applied, by the way. We then imported the video into Tracker and retrieved the data that we used for the graph we plotted on Excel. We will later show that graph when comparing the experimental model to the theoretical model. But for now, here is the video. Moving on, here's the GlowScript code that we used to create the theoretical model. We first used the equation on the left to obtain the value of the average velocity. The initial position, final position, and time values were all known, so we were able to calculate the average velocity easily. To the right, we have the code. We first altered the values of the initial position and the velocity from 0 to 0.789 and negative 0.692. After that, we changed the condition in our loop to t is less than 1.435 because that was the duration of our video. Note here that the Fnet value is 0, and that's because the acceleration is 0 and the velocity is constant. Was also why we didn't update the velocity in the next annotated line. As for the position, we updated it by manually multiplying delta t by the velocity. However, this can also be done automatically simply by typing in ball.velocity multiplied by delta t. Now, going back to the Tracker equation on the left, we can see that it's in the format of y is equal to c plus mx, which is the known format for a linear graph. We can automatically see that our graph will be a straight line with the average velocity as the slope. Here's a theoretical model. As expected, the velocity time graph is a horizontal line representing the constant velocity, and the position time graph is a linear line representing direct proportionality. We also already know that the slope represents the average velocity, but we can further confirm this by looking at the units. The slope is equal to the change in y values over the change of x values. The y values are in meters while the x are in seconds, meaning that the slope will have units of meters per second, which are also the units for velocity. Now let's compare our models. Here's a graph representing each model. The blue represents experimental and the orange represents theoretical. Automatically, we can see that the slope of the blue line is changing initially. This indicates that the cart is accelerating. The slope then becomes fairly constant until it reaches the end where the cart slows down, causing the slope to flatten. At the very end, we can see that there is a gap in the final displacement of the theoretical and experimental models. This gap accounts for the fluctuations in velocity in the experimental model. This shows that the cart moved a total distance less than what was expected. This could be because of multiple reasons. Which leads us to our next slide, possible sources of error. We made a few assumptions in this experiment, including negligible friction and air resistance. But what if friction had a bigger effect? It would mean that the velocity would have fluctuated way more than it actually did, because the forces on the cart won't be balanced, causing there to be a net force, hence an acceleration. Furthermore, what if the track was slanted? That would mean that the weight acting on the cart would have had a component parallel to the track that caused the cart to accelerate. For our final discussion, we'll answer a couple of questions. First, what if the axes were flipped? The magnitude of the velocity and position would not change, but their signs will switch. This means that the graph would have a positive gradient instead of a negative one, and the graph would be reflected over the x-axis. Second, is it possible for you to say how many pushes and pulls, i.e. how many forces, are added together to give zero net force in the case you observe? It is not possible, as we have made multiple assumptions regarding the forces acting on the car. Furthermore, there may be sources of error causing extra unknown forces to act on the car, as mentioned in the previous slide. That's it for today, and thank you for listening.